Next, let's move on to the introduction of evaluation pipeline, the state-of-the-art algorithms and code bands and Docker summation. So, Zdravko, hand it over to you.
Thanks, John. Let me just share my screen. All right,
Yes,
everything works, right?
yes.
Perfect. Yeah, thanks for the nice introduction, John. So let's move on to the evaluation pipeline. I'm very happy to represent KIT at this challenge, and let's get right into it. So this year, we really want to focus on iterative interactions, which means that you have a model that iteratively improves when you provide more and more information to it in terms of interactions. So as June presented earlier, last year, we focused on bounding boxes, which are just one interaction. But this year, we really want to do this iterative refinement. So the illustration of how we implement this is on the left here. The first step would be to generate the initial interaction. That's a simulated bounding box, which is done for each of the classes in the image. So you start off with the image and the label, and then you just generate the pre-computed bounding box. And that's part of the input of the image. So we start off with n bounding boxes for n classes. And then this is provided to the model, to your models, and your model will produce a prediction. This prediction will not be perfect. And this is exactly the motivation to also apply clicks. Clicks are something that could be iteratively accumulated as interactions, whereas bounding boxes are just single shot prediction. And to simulate that, we have a loop. So we look at the error which the model has made, compare it to the ground truth. And for each class, we compute a new click based on that error. And we repeat that m times, or m equals 5 in this challenge. So we have m times n clicks for the whole image in the end. And we look at the prediction at each one of these intermediate steps to compute the interactive metrics, but I'll go over that in a second. And the final step would be to look at how the model annotated that data set with 6 interactions, the bounding box, which is optional, and the 5 clicks. And this leads to the final performance of the model. To give a concrete example, let's look at the CBCT scan of the alveolar canals. And here you can see you start off with a bounding box. Let's say it produces a very bad prediction. Then you simulate a click on the error and it becomes a bit better, but you need more and more clicks. So you add more and more and more until you reach the number of 5 clicks, which is the maximum number of clicks. Let's say we have something very good and the curve looks like this and it increases with each click. This is what the method should be doing at the end. The way to actually capture this refinement in a metric is, for example, to just look at the area under the curve. If the models produce good results and increase their performance on each one of the new interactions, then you would expect this area to increase as well. The same goes if the models have started off quite well for the first interactions and then also steadily increased. The area is just a scalar that captures all of this into one single metric. In essence, that's how quickly do you annotate the image given a number of interactions. And an even simpler metric is to just look at the final performance of the models after all interactions, and that would be the annotation quality. The nice thing about this is that you can apply it to any metric. It doesn't need to be just the die-score. It could be the NSD or the Hausdorff distance. But for this challenge, we keep it simple and just use the NSD and the die-score as the last CVPR 2024 challenge. So all in all, we have 2 areas under the curve and 2 final metrics. So this gives us 4 metrics per image. I just want to reiterate what John already said. The bounding box prediction is optional. So you could use it, but you're not obliged to use it. It's additional information that could provide you a better initialization of your model, but you can easily just skip that interaction and just provide maybe an empty mask. And we only compute the area under the curve for the click-based predictions. So this gives a fair advantage to also participants which do not use this bounding box. So how this evaluation actually looks like for a single image, you look at all of the classes in the image. Let's say we have n classes, and you compute the 4 metrics for each class individually. Then these metrics are averaged to compute just 4 metrics per image. So you might have n classes, but you collapse them to 4 metrics at the end. And for each team, you go also over each image, but we use the rank and aggregate strategy. So instead of averaging the metrics, we average the ranks. So we form 4 ranks per image, repeat that for all of the images on the test or validation data, and we average the rank at the end to rank the participants. So another question is, how do we actually simulate these clicks? For the bounding boxes, Jun already explained that we have this very fixed pre-simulation scheme, and this could be pre-computed for the challenge. But for clicks, you need to do it dynamically since it depends on the error of the models. So a very abstracted way to look at how clicks are simulated is to take a look at this pseudocode here. We start off, for example, with the bounding box prediction, and we have some error. The first thing we do is we find the largest error component, which could be aggregated by false positives and false negatives. Then we compute the Euclidean distance transform. Here you can see the global Euclidean distance transform, but we actually compute a localized one to make it more efficient and to also concentrate on a single area. And then we sample the maximum values of that Euclidean distance transform, and that leads to centralized clicks in the error regions. And we repeat that for also the next click. So we use the click which we have sampled, we give it as an input to your models, and then we look at the next error and the next one. And here on the bottom, it should become better and better when adding more and more clicks, and the components should become smaller and smaller. And repeat that 5 times. So we already also went through the format, but for the evaluation, we also need to go into how clicks are encoded. So we have the MPZ input files, we have the images of the IMGE's key. We also have the boxes, which Jun already explained quite well. But we also have the clicks, and they're stored in a dictionary that stores foreground and background clicks. And these are just a list of 3D coordinates which represent the clicks. And we also provide an additional input as a click order. So we kept this throughout the last month. But we also have this click order to help you establish how the clicks were actually ordered in the image. And we also give the previous prediction, which your model has produced in the previous iteration, to make it possible to inform your model and make consistent improvements. And as a final thing, how do we actually evaluate? There's 3 paths to do it. One is directly through CodaBench. There, you only need to upload your predictions. Basically, let your models run. You can simulate the interactions using our iterative script, and then upload your predictions to CodaBench as a zip file. Then you would only have 2 metrics. This would be the last dice and the last NSD score. So you cannot really have this iterative improvement and logging of the intermediate predictions. And you can do it 5 times per day. Another, the more official way to do it is to send us an email, and we set very fixed deadlines every 10 days, where you send us your Docker container with your team name, team leader name, and say it's a validation submission. And we will evaluate that ourselves with the evaluation script on the validation data and the ground truth data from the validation. This will give you a very good picture of all the 4 metrics, but also it gives you the opportunity to debug your methods on the validation data before the actual test phase, which would be the same way as the validation phase. And finally, you can also do it yourselves. You can just run it locally. We do provide the validation script when we're updating with new features throughout the competition. And you can use it to just cross-validate your approach on the training data. And as a final remark, another thing is that we also have a time limit per image, which is a very generous threshold of 90 seconds per class per image. And so far, all of the baseline contributors very easily pass through all of these thresholds. And with this, I think we're done with the evaluation pipeline, and I think we can move on to the next topic. Thank you.